right, at this point we want to look at a system of quadratic equations. We've solved systems before, and remember that when we solve systems we are looking at two or more equations that share a common solution. If you look at them on a graph, you're looking for the point of intersection. So let's set up a system of equations that contain a quadratic. If I've got a system that is defined as y is equal to negative x squared minus x plus 6 and y is equal to x plus 3, we can solve that system of equations. Well, look at the difference from what we've done before. Instead of having two lines here, I have a line in this last equation, but this equation is going to graph as a parabola. So I'm looking for the point or points of intersection for this particular system. Now think about something here. If I have a parabola and a line and I choose to look at where they intersect, I could have a couple of situations. I could have a parabola up here and then a line way over here, and they could never intersect. It is possible for them to non-intersect. They can intersect at one point. You know, I could have my line could come down through here and could just barely touch my parabola, and I can have one solution. Or I can have a situation where when I cross twice. So I could be looking for no point of intersection, one point of intersection, or 2 points of intersection with this system. And there are a couple of ways to work this, and you should be familiar with both, but then once you are, I really don't care which method you use. The first thing we can do is solve this algebraically. To solve it algebraically, let's set these two equations equal to each other. And I'm going to put the line on the left-hand side because, you know me, I like positive x squared terms when I get done, and I like things to be on the left-hand side. So we're going to move our negative x squared minus x plus 6 to the left. These are equal to each other. You're looking for the point of intersection. They should both have the same x value. So if I add x squared to both sides, I get x squared over here, and it goes away on the right. Add x to both sides, I have plus 2x. And subtract 6 from both sides, I have minus 3. So now I've got a quadratic in standard form. X squared plus 2x minus 3 equals 0. And I can solve that using any method that I want to use. I can factor it, I can graph it and find the solutions, I can use the quadratic formula, I could even complete the square. Well, I like to factor. Multiply to give me negative 3, add to give me 2, because my a value is equal to 1, I get x minus 1 times x plus 3. And that's going to give me the same quadratic if I multiply it back out. So there are the two factors in my quadratic. Set those two factors equal to 0 for solutions. Important concept, never forget that one. If you set your factors equal to 0, you get the solutions to your quadratic. You get your x-intercepts as long as they are real numbers. So I have x equals 1 and x equals negative 3. Well, when we're looking for a solution to a system, we're looking for a coordinate. We're looking for an ordered pair. I need my y value. So I'm going to take this 1 and plug it back into the simplest of my two equations. I'm going to put it back into y equals x plus 3. Well, when I do that, 1 plus 3 is 4. I get y is equal to 4, which means my first point of intersection in this graph is 1, 4. I also have to do the same thing here. X plus 3 equals 0. X is equal to negative 3. If I take that negative 3, I plug it back in for my x, I get a value of 0 for y, and my point of intersection is negative 3, 0. So algebraically, I have discovered the 2 points of intersection for my system of equations, one of which is a quadratic. But there's another way I can do this. I can graph this. You can do this on your calculator, or you could come through and actually graph this by hand. So really quickly, I'm going to sketch out a graph here and show you what you get when you set up your graph for this system. And let's put a few units on our graph. So we're going to say these are marked off in ones. 1, 2, 3, 1, 2. and 3. This line, the y-intercept is 3, the slope is 1, so I'm starting here, I'm going up 1 and over 1. So here is my line, my quadratic. If I compute the vertex, I end up with a point that's way up here. I have a y-intercept right here at 6, so we reflect that across the axis. Plug in a few more points, I discover that I have those. My x-intercepts are going to be here, and then if I graph my quadratic, and you can do this on your calculator if you want, my quadratic is going to look like this. So what am I looking for? I'm looking for the points of intersection. Well, I have a point right here, and I have a point right here. This point of intersection is this 1, 4 that I found down here with x minus 1 is equal to 0. And this negative 3, 0 point of intersection is the point I found with the other x value. Now, if you want to do that on your calculator, remember that you can go to, on your calculator, once you have graphed both of these, put one of these in y1, put the other one in y2, press graph, get the picture where you can see it, where you can see your points of intersection, and then you can do second trace, which is the calc button, and look for the points of intersection. So I can do first curve, second curve, guess, and first curve, second curve, guess, and it will give me these two values using the calculator. It's fine with me if you use the calculator to find those, as long as the instructions don't specifically say to show how you did it algebraically. Also remember, you could have, instead of having 2 points of intersection here, you could have just 1 if we came down through here and looked and it just barely touched, or you could have none if this line never crossed your parabola. So solving systems with quadratic equations when one of them is a quadratic.